Hi and welcome to this video about writing a simple reverse shell. So first, what is a reverse shell anyway? So if I just launch something like cmd.exe, I get a shell. This is a normal shell or a forward shell if you will. A reverse shell is a shell I can control from another machine. So essentially what I want is to have this controller machine where I have my own application that's going to allow the user to input various commands suitable for a shell. And then on the remote machine, the machine I would like to control or have insight into, there's some kind of application I'm going to write called remote.exe just for demonstration purposes. And this is the one that's going to function as my go-to guy when I pass commands that should be invoked in a shell. And so the local exe and remote exe are connected through the network. And when I issue command to remote, it's going to use the normal Windows shell, cmd, to parse those commands and execute them. And then any kind of result is going to be returned to that remote exe and going to be forwarded back or returned to the local application. So essentially I'm going to use a normal shell, but it's actually going to run on the remote machine. That's the idea. And for that, we have to write these two applications. I'm going to call them local and remote for simplicity. Of course, in their final names, the remote at least probably have a different name to make it more confusing, such as svc host or even cmd or something that is not suspicious. But for now, we'll use these names to make it easier to understand. So let's begin by writing the part which is local to my machine. And so I'm going to have a Visual Studio project here. I'm going to use two projects. The first one is going to be the local project. Let's just create a simple console application. Let's call that local, a very simple name. And I'm going to give the solution the name reverse shell. So we'll have two projects there. One of them is called local and the other one being called remote. So let's start with local. The purpose of local is to listen to a connection coming from some remote machine and then connect to that machine and then start to send commands and receive information from the process on the other side. So we'll have to do that, and then we'll see how to properly implement the remote executable, which is a bit more complex. So first we're going to need to do some networking stuff. So we need to include winsock 2.h. Now, one thing we typically do is include windows.h as the first thing to do. This is not going to work out as you might expect. And the reason is that if you include windows.h first, winsock 2 will not properly compile. If I try to build that, I get this gigantic list of real errors. What you need to do really is to swap the order. And the reason is that winsock 2 actually includes windows.h as well. And so we don't actually need windows.h, we just need winsock 2. So that would allow us to properly compile stuff. So now we can start by first initializing a winsock. And so I'm not going to talk about winsock too much, just see the basics, and we'll use the simplest functions we can get away with in order to do what we need to do. So the first thing to do is to initialize winsock, and this is done using the function wsa startup on Windows. We need to provide the version as a word, that's a 16-bit value that is comprised of two 8-bit values, the major minor numbers, and 2.2 is the current version for winsock. And we get back this result, which is just providing information about the winsock library that we have on this system, which we don't really care about. The return value is some error, which is just an integer, and 0 means success. I'm going to just use little asserts here. I'm not going to do any kind of error handling where we don't need to do those for our purposes, just to make things easier to use. So just assert is going to be good enough. If something goes wrong, we'll run this thing in debug and we'll get an assertion failure. The next thing to do is to get a socket we can work with. So let's create a socket using this socket function. That's the classic function that is still coming from the Berkeley sockets, the original socket standard, and which is also implemented by Windows. So you want the IPv4 here. I'm going to use IPv4 addresses. We want a normal TCP socket. So sock stream is going to be the constant here, and the protocol is going to be TCP. So once we have that, again, we have in this case a socket object is just some kind of handle. So I'm going to use assert here, but this time the socket itself is going to be something which is not the invalid socket. This is a value which is -1, indicating some kind of error. So we have a socket here, but this socket is kind of in the air. It's not bound to anything. So we have to bind it to some address locally so we can start listening on that socket. So we need to first specify some address information. So I'm going to have this sock address IN as the structure. This is appropriate for IPv4 addresses. So let's start with the family here, which should be AF INET, address family INET. This means IPv4. And we need to select some kind of port in order to listen on the local machine. And for that, I'm going to select something that I know it's not being used on my machine, which is going to be these 5, all 5 kinds of port. And we have to use this function h2ns that hosts to network, and S is for short, that is a 16-bit value, because we need to convert that from the host representation, which in this case is Little Indian, because I'm running on an x64 system, to network byte order, which, by the way, uses the opposite, the Big Endian encoding. So in order for me not to have to deal with that, I'm just doing h2ns. So if the host happens to be something like ARM64, which can use Big Endian, is going to do nothing, but in case of Intel, it's going to swap these 2 bytes representing this port. And once we have this, we don't actually have to provide a specific address. There's no need. It's going to be picked up randomly by the bind operation, which is going to be our next step. So we want to bind this socket, which is currently just pointing to nothing, to the address that we built right here, with the appropriate protocol and all that. We need to do some casting here because there's a kind of a base structure, but since it's all C, it's not really a derivation, but it is an extension logically. We need to just do this kind of casting for the compiler to be happy. So let's go ahead and do that, and again assert that this thing works. And the next thing to do is to listen on this socket. So we're going to use listen here. And backlog just indicates how many concurrent connections I'd like to have in my queue. So let's just go with 1. We just need the 1. And so this is just a simple listen, saying that I would like to make this socket listenable. And then we need to actually wait for a connection to be available. And this is done using the accept function. So accept is going to block. I'm always going to use here synchronous calls, so I don't have to deal with asynchrony. It's going to be much simpler, and I want to use the simplest code I can get away with. And what accept does, it accepts this listening socket that we created here. And then, of course, we can provide an address, but actually that address is a return value. It's not really an input, it's actually an output, which indicates what the connection on the other side is. We can specify null that indicates that we don't care, and that's definitely one way to go. We just want to get the connection here, and the return value here is actually a socket, a new socket, which is the one that needs to be used in order to actually facilitate communication. And so we need to make sure that, of course, this socket is a good one, and it's going to block until that thing is going to be available. Just before we do that, let's add some information here, like waiting for a connection, like so. And I'm going to include here for stdio. And I also want to display the actual address we get back. So we can utilize the same address here, the same address structure. We don't need it anymore after the bind operation. So we can pass in the length of the structure and then provide here the address so that it could be filled by the API. It requires here the length as an address. It's going to place in there the actual size of the returned information. And just like before, we have to do this casting to make the compiler happy. So once this works and we get a proper socket, we can say that we are connected to, and we want to provide the address here in some good way to represent that, to display that as a string. And since we don't want to do the actual manual work here like manually, and there is a helper function we can use. So one of them is called, there's a header called IP2String, and there's a function here that is actually part of NTDLL, which is kind of unusual, but still, it's called RTL IPv4 something address to string A. I would like to convert that to an ASCII string, but I could have converted that to Unicode if I wanted to. So let's create a buffer here to take the result. And this function requires the actual address, so we have that here. And in fact, we have to get to the actual address, not the whole structure, which also has the address family and stuff like that. And the result is going to end up in address. So now we can go ahead and add the address here, like so. And this would show us what are we connected to. So now that we have a client connected, that's supposed to be our remote process on the other side, on that other machine, we can start talking to it by receiving and sending messages. And before I actually do that, just to show you that what we've done so far has some meaning, we can see that we want to see that in fact it is listening on this particular port for my process. So first let's try to build this. This will not beat successfully. The compiler is happy, but the linker is not. And that's because we have to link against the libraries which are not specified in the link list of libraries by default. One of them is for the Windows sockets. That's the first one. And the second one is for NTDLL. Since we are using one function from there, I don't want to get it dynamically. It's just going to be easier to just link to the import library. And now, in the very least, it works in the sense that it compiles and links. Let's go ahead and press F5 and try to run this. So once we run this, you can see there's waiting for connection. So how can we actually tell whether it's actually waiting on the correct port and all that stuff? I'm going to launch a tool called TCP View from sysinternals. If you launch that, it will show you all the open TCP and UDP connections right now. So let's see, the application should come up. Here it goes. So here's what that looks like, and I'm going to just do a filtering here. We have this application called local. So you can see there's a listening TCP here that listens on port 55 on all fives, and this is our application, of course, and it looks fine. We don't have any local address, and that's okay because it's being taken randomly, so it's not shown here. At this point, we haven't yet have a proper connection connected to this server, but at the very least, you can see we're listening on something. And there's nothing on the remote side. There is no remote address, there is no remote port just yet, because we haven't yet connected to anything. So at this point, there's nothing else we can do. We can just go ahead and stop this application. So the next step is to start talking to our application on the other side. So we need first to have some kind of buffer we want to work with. That's where we're going to get back information. So I'm going to use, let's just create a big buffer, like even 1 megabyte, a relatively big buffer, by calling the virtual alloc function to create this buffer. So we have the size here. Of course, we can use something simpler like malloc or things like that. It's a bit more efficient. It's more efficient to use virtual alloc for big allocations, but not terribly important for this example. So we have this buffer, and again, I'm not going to do any kind of interesting error handling. And we can now start with an infinite loop. So what we want to do is first to get information from the other side. And why am I receiving information first? And that's because when you launch CMD, CMD has some output initially, so let me launch CMD for a moment. Here's what CMD shows by default. It shows some information about the Windows version and provides the prompt here. And so the first thing we want to do is to be able to read this information from the other side. So I'm going to start with the receive operation. Receive operation, we need to provide the socket, that's S that we are bound to. So that's the local socket that we bound to this particular client. The original socket can continue listening if you want that to happen. And then we have the buffer we just allocated, and the length of the buffer is size, and no interesting flags we need to have right now. So if byte is less or equal to 0, it means there's some kind of error. If it's 0, it means that the connection has been closed, so the remote process, the socket there was closed. If it's less than 0, if it's -1, it means there's some other kind of error, maybe networking error, maybe something else. So regardless, what that does, if everything goes as planned, returns the number of bytes that we actually receive. So now we can go ahead and just display whatever we received, just by displaying buffer here to our console. This will be our remote shell. This is our like the local UI we can use in order to control the remote shell on the other side. And so now, once we display that, we want to get some input from the user. So let's have some input here. Let's say 256 characters is enough. Let's get some input, and then send it to the other side in order for it to be actually executed on that CMD somewhere. So we're just going to use the send function. We're going to provide our socket, the buffer is input, and the size is going to be the string len, of course, of input. And maybe also we can send the null terminator like so. So that's almost right. Unfortunately, we have to do something else. One of the things we have to do is to append to input a \n. Because as the way that getS works, it waits for an enter, but it doesn't have the enter, the \n at the end of the input. And this is important because otherwise CMD will not know that it actually needs to execute something. So we have to do something like this in order to append that n. I'm using strcut, the safe variant, to add that to whatever input the user has provided. And then we can send that on its merry way. We can do a little sleep here just to let things like not receive very quickly, let some time for the other side to get that response. It's not really very scientific of me to just use some kind of random looking sleep, but for this simple example, that's going to be good enough. And that's all there is to it for the local side. Of course, we might need to do some cleanup. I can also do something like maybe compare the input to the text exit. And if this is the case, we want to perhaps break off this loop as well. We might want to do that perhaps after we actually do the send. And the reason is that we want that exit perhaps to propagate to the other side, so that CMD is going to be exiting as well, so we don't leave much of a trace. And that should be it. There is some, again, cleanup we need to do here, but it doesn't really matter that much for our purposes. It's just this local application. And it's going to shut down very soon. So it's going to free all the memory, close all the sockets, all that stuff is going to happen automatically. So we're good to go for the local, at least. That's how it seems. Let's go ahead and create the more interesting application. That's going to be our remote application. So I'm going to create another console application called remote. Again, to make it easy to make the distinction. So in terms of remote, what do we want to do here? Let me go back to the slides here to discuss a bit more detail as to how we're going to implement that stuff. So here goes. Now we have this local exe already working for us. Now we need to write this remote.exe. And it's going to communicate with CMD, which of course is built in. We don't have to do anything about that, but we do have to communicate correctly with CMD so that CMD does what we expect it to do. So here's what we're going to do. There are a couple of ways we can implement that. I'm going to select just one of those ways. So I'm now focusing on the controlled or the target machine. And we have two processes there. We have CMD, of course, which is built in, and we have remote, the one that we're going to write. And so remote is going to create two pipes, two anonymous pipes that are going to control and be able to read and write information related to CMD. And so what would happen here, we have anything that CMD writes is going to be read by remote, and anything we want to tell CMD, such as issuing commands, we're going to write it through the other pipe. And hopefully CMD will do what we need. So we have this bidirectional communication between remote and CMD. So we need to make this work in this particular scheme. Okay, so now that we understand hopefully better what we're trying to do, let's go ahead and do that. So the first thing is that we, of course, need to have the usual includes for WinSock2. We need networking here as well. So again, no need to do anything else. We have an ability to use an assert here for debugging purposes. We might need some other things, we'll see. Well, let's add a string here. We're going to need a string here, so we're going to use that as well. So in terms of command line, we might need to grab a command line argument, which is going to be the IP to connect to. And the reason I'm doing that is that I want to first test locally. If I can test locally correctly, then at the very least I know that my logic is okay, and the only thing I have to test now is the true network. But we'll do true networking anyway, but we can start with a local variant. So we need some kind of address. Let's do that as a character star. So we need some kind of address, and we can look at argc. If it's greater than 1, we'll grab whatever argv1 has to give us. Otherwise, we'll use the local system IPv address like so. So with that, we'll be able to use local code or non-local code depending on what we need. So now that we have that, we can start to do the actual work. So first thing, I'm going to do some copy pasting here. We have to initialize WinSocks. That's the usual stuff there, nothing special here. And the next thing to do is to actually connect to the target machine. And so the next thing is to create a socket just like before. So let me just go ahead and copy this code as well. But now we're not listening here. In fact, we want to do exactly the opposite. We want to connect. So we need to, in this case, just like in the previous one, need to prepare some address. So let's call it ADDR. And in this case, the scene, family, and all that stuff is the same. So it's IFINet, that's IPv4. And the port, of course, is the same. We need to connect to that port specifically. So we're going to use H2NS with the port. So that's all good and well, but now we actually need the address as well. We need to provide the address, and we want to use a function here called inet p2n. It allows us to convert the string-based address to the actual bytes, representing that in network byte order. This requires another header called ws2 tcp/ip, something like this. Let's see if that exists. There is something like this. So here's the function. We need to provide the family, which is of course AFINet again, the actual address as a string. So we have that from the command line or the default that we selected. The finally is the actual result, and the actual result should land in addr.scene address, which is where the actual address is stored. So hopefully this would be fine. If not, of course, we'll find that out at runtime. The next thing to do is to connect. This is where we connect to the other machine. So we have our socket, which is currently unbound to anything. We have the address, which we spent some time filling in. And then we have the size, which is the size of the structure. Not very interesting, but still something we need to do. And again, this thing should work. So if it works, we get back 0, indicating everything is fine. So if this is fine, now we have a socket we can work with in order to send and receive information. However, we're not nearly done. We're not ready yet to actually do the communication with CMD. First, we need to create it. But before we do that, we have to create these two pipes that I was mentioning. And so for this purpose, we need to do a few things. First, we need to provide handles. So we have the local read here. That's the read in our process. That's going to be the input read from our process. And we'll have a CMD write. That's going to be the write we're going to pass to CMD. And we're going to create a named pipe, an unnamed pipe, using the create pipe function. The create pipe function creates a pipe with two ends of the pipe. We have the read end and we have the write end. We need to provide security attributes we can normally specify as null, but in this case, the way we're going to pass some of these handles to to CMD is by using this feature called handler inheritance, which I think I've demonstrated in another video. So in order for these handlers to be inheritable, there are two ways of doing that. One of them is by creating a security attributes data structure and filling the first member as the size of the structure, and then I'm not going to change any security setting per se. I'm not going to create any security descriptor here, but I have to specify inherit handler has 2, which means that when I create a new process and specify these handlers, they're going to be duplicated into the target process, like so. And size here means I'm going to create something which has any kind of size that I want. So we have this first pipe that has these 2 ends. We need, in the same idea, we need a second pipe. So the second pipe, we have a CMD read. This time it's going to be the read end being provided to CMD. We've yet to do that, but we'll do that very soon. And then we have a local write. We're going to use here locally to write to CMD, to that other end of the pipe that would then go to CMD. So again, I'm going to call create pipe here. This time with these new handlers, we have CMD read. These also need to be inheritable. And here is going to be our local write. So we have these 2 pipes available and ready to go. They have these 2 ends. Each one has 2 ends. We have 4 handles in general. And now we're ready to create our CMD process, which we'll use to communicate by sending commands and then reading responses. So in order to create the process, we'll have to do some preparations. So we have 2 structures for process creation. One of them is process information, which is going to be the result. And then there's also startup info, which is where we're going to set some parameters. Normally we just zero out the entire structure and set the size in the first member, but this time we need to do a little bit more. We need to, in this case, make sure that these handlers, the appropriate handlers, are going to be inherited and passed and duplicated to CMD. So the first thing to do here is in the flags indicate that we would like to use this particular mechanism. So that would be std handlers. So use std handlers means I would like the function create process that I'll be calling very soon to actually take note of this information. So we have the std error and std out. This is the output. That's going to be the handler I'm going to pass to CMD. That's going to be hcmd write. CMD is going to use this handle to write to it. Now we'll read from the other side. The other side is is h local read here. And then for the input, so we have std input is going to be the other pipe with the read end. So we have CMD read. And now we're almost ready to call create process. We need to prepare the process name. It's going to be cmd.exe, and I'm going to use the /q here to prevent CMD from echoing back every command we write. Let's make it just easier to see the results. And then we can go ahead and call create process. So let's go. Here's create process. The first parameter is not important. The next one is going to be our command line. It's going to be name. With the entire cmd.exe and the command line. Some security attributes we don't care about, like so. And then we want to create this thing completely hidden. We can use something like create no window as a flag. But before we do that, there's another parameter here we choose inherit handles. This is the point here. We have to make this true. So these handles that we've specified are going to be traversed and in fact duplicated into the target process. Without this true, these handles will not be duplicated and will lose the connection that we want to establish to CMD. We don't want any window to appear, so we can use create no window for that. That should be good enough. And then some other parameters which are not very important. I can perhaps use this current directory to start at C:, but it doesn't matter. We can start anywhere. And then, of course, we're going to provide the startup information and the process information right here. So if created worked, and it should, then we have a CMD working for us, and we can actually start doing the real thing, which is to start communicating with the other process. So first thing, we need our own buffer, perhaps, to get information, to read information from CMD. Let's go ahead and create a buffer for this purpose. Again, I'm going to use a virtual alloc here to take a fairly big buffer. So let's go with some kind of size here. Let's go with 64 kilobytes, like so. So we have null, we have size, we have mem commit and mem reserve, and of course page read write. So this is just some preparations. We want to have this buffer available to us. The next step is to start a loop, an infinite loop, for as long as we have a socket open on the other side. Maybe we'll be able to figure it out later on and know when we can exit that, but it's not super important for our purposes here. And we need to have some result string here. Let me just have string here. Probably don't need that on the local side, but here we might need that. And so the thing is that what I want to do here, I would like to read from the pipe. The problem is that I don't know if there's any data available. If it's not available, the call is going to block because we're going to use synchronous calls. So what I'm going to do, I'm going to use the function peek named pipe. And so peek named pipe allows us to peek at a pipe to see whether there's information available. Now the name is a bit misleading. It's called peek named pipe, but in fact it works with anonymous pipes just as well. So you can specify here the local read, the one that is connected to the read part on our side. We want to see whether there's some information that CMD has written into its right end. So I want to provide some, we don't really care about the actual data, we just want to know if it's available or not. And so we have these total bytes available. This is what I want to know. So I'm going to have some value here. And so if this one returns true, which means that the pipe is still alive and it's not broken, so CMD has not terminated for some mysterious reason, and bytes is greater than 0, then we want to do something. So let me write these bytes here, like so. Let's do that. And now what we want to do here is to actually read. So as long as there's data, let's actually read the data. So peek doesn't remove any kind of data. Normally it just gives us information whether there is data available. And since there is, bytes is greater than 0, we can just actually read that. I'm going to read that value into buffer. We have the size that we can accommodate. We get information indicating how many bytes we actually read, which is actually important. And we're not going to do anything asynchronous here. So reading the data, and the data, since it's actually text, but still it's just a bunch of bytes, it is not null terminated. So we have to null terminate it. So let's use buffer at index bytes and put a 0 there to null terminate that. And just propagate that and append that to what we have in result. And then we can do a little sleep here to make sure that that if CMD is working a bit slow, it can be ready to send the next chunk. So we might need to have multiple calls to this peek named pipe until there's no more output coming from CMD. This is just something I found out by doing some trial and error, basically. So maybe this code is not perfect. It requires perhaps more testing. So once we have that, we can go ahead and send the result. So we're going to use the send function with our socket. The buffer is result.data.cstr, really, that's the pointer. And the size is result.length, the size of the buffer. And no need for any special flags. And of course, we have to cast it here for the function to be happy. And we're sending that information. Once we're sending that information, we want to get back from our client on the other side where the local executable is running, whether there's commands a command to send to CMD. So we're going to use the opposite function now, receive. Let's receive information, if there is any, until we get something. This call will block. And so I want to get back here some kind of input. So we can create a little buffer here, but doesn't really matter that much, but let's do that anyway. So we have some input here, let's say 256 characters, as we've seen on the local side. Let's see if we get these characters. And once we have that, if received is, in this case, we can check if this is less than or equal to 0, then something went wrong. Maybe the other side is gone, so we want to just break. Otherwise, we know that we have something to do, so we can write that to the other end of the pipe, to our local write, so it reaches CMD. So we have our input here, and of course we need the string length of input, and cast that to dword for the compiler to be happy. Sometimes it's pretty pesky. Number of bytes we actually get back, we actually have written, is not really that important, but you have to provide something here, and we're doing everything synchronously. And then we can do again a little bit of sleep to let CMD do its thing before we go back and peek for yet another output, which should be available based on the command we specified here. And that's basically all there is to this loop. And again, we can break here and do some cleanup, all that stuff, but I'm not going to bother with that for simplicity. Okay, so let's build this, see if it works as we expect. And apparently it's not, so let's make sure that it does, something like this. And again, we have the usual stuff related to NTDLL. Well, actually not NTDLL, it's actually the WinSock, the one that we need. We don't have any NTDLL functions here. So now, in the very least, it compiles. I mean, we have to start somewhere. Okay, so now let's see if we can actually do something about that. So what I can do is to go to the properties of the solution and decide that I'd like to have multiple projects and all of them starting with a debugger, like so. So we're going to press F5. You'll notice that the solution is now in bold rather than one of the projects. I'm going to press F5. And once I do that, I should have two processes coming up. So you can see we have waiting for connection here, and it's actually connected. Some CMD should have been created here somewhere, and we should have actually seen something happening here. And apparently we don't. So something seems to be wrong. So one thing I can guess, let me stop this. So of course we can do more debugging, but I don't want to waste much time here. Let's see if the result here is empty. If it's empty, it means there's nothing else available just yet. Let's just continue and try this again. Let me run again by pressing F5. We'll run both of these processes together. So here goes. So now it seems to work a bit better. We can see here that we get the output here from our local. Remote, of course, usually is going to be hidden, which is going to be something we'll do later on. But for now, it is visible. Notice in TCP view that we have these two connections available here. So there's a connection here. So this looks fine. Let's see if we can write some commands here. So if I do something like, say, dir, I can see the directory output here. And of course, it might seem not very impressive because, I mean, really, we're just doing these things. It seems to be local, but it's not. So this is not CMD. It actually is working with a hidden CMD. To see that a bit better, let's go ahead and make sure that we, in fact, display the CMD that we create. So I can do here another printf saying CMD created, and its PID is whatever is provided here with DW process ID, which means that this process is very much alive. So we'll see that in the remote part. So here goes. So again, we're launching both of these together. You can see that the PID is 66196. If I open Task Manager here, we can see that we have a bunch of CMDs here. This is this particular CMD. And we can see more information if you want to look at the actual handles, all that, using Process Explorer, but I'm not going to do that right now. Let's now go ahead and move to the next step, which is maybe to hide remote completely. We don't want actually to see it. So remote here, we want that to be completely hidden. We don't want that to be a console application at all. So I'm going to go back to remote here. And well, there are a few ways of doing that, but let me just change the application from console to being a Windows application, meaning that a console will not be created automatically. So now if I try to build this, it's probably not going to build out correctly because we now have a different thing on our hands here. We need to make sure that we have a WinMain function. So let's go ahead and change that to WinMain. So we have in WinMain H instance, another H instance. I'm not going to use them, so I'm not going to bother naming them. And there's the command line. This is the thing that we're interested in, and some parameter, which is again not very interesting. So now the address should be different. So we're going to take CMD line. So if CMD line is not null and CMD line dereferencing that is not 0, then we want to take CMD line in itself as the address. Otherwise, we're going to grab 127.0.0.1 just like before. So now if I try this out, if I run this, I run both of them now, we don't see remote anymore. So there's no window for remote. It is still there, so I can do stuff, like do things, and that's it. So I can go ahead and do these things for as much as I like. And apparently there's some kind of bug here. There's still another bug here, which I have to probably fix. Let me see if I can figure out what's going on. Okay, so I had a little bug here. We have to zero out the byte here. So because otherwise buffer might contain a longer output from the previous part. So now it should work just fine. Let me run this again. Again, we have just the local part. We don't see the remote here. It is of course running. So if I open Task Manager, here's the remote. It's here, but we don't see it. And it's communicating with a CMD, which we don't see. So we have dir here. I can change to D. I can change to some other directory, this stuff. It all works fine. I can even use exit to exit everything. So now the final piece of the puzzle is to remote that stuff. So I'm going to go to my Explorer, open that up. So here goes. We have the local and remote here. I'm going to grab remote, and I have here a virtual machine. I'm going to paste remote here. So we have remote here. We just need to set the correct IP address. I'm going to ping my machine with its DNS name. Okay, so we have the IP here. So let's go ahead and use remote with this address. Before I do that, of course, I want to run my local thing here to start listening. So now we have local listening for a connection. We can see it here. And we hope to connect to this remote thing on the virtual machine. Let's go ahead and do that. So of course, I'm in the wrong directory. And you can see remote exiting, which is fine. We don't, it's not remote. Remote is not really important in itself. It is important to communicate with CMD. So remote is in fact there. It's still running. We just have CMD here returning. If I open Task Manager on my virtual machine, we should see remote here. So here's remote. It is here. And there's some CMD that it's working with. So we have a bunch of CMDs here. At least one of them is the one that it's working with. We can't tell perhaps directly because we don't have any output here, but it is one of them for sure. And it's supposed to be working now. So if we look at TCP view locally, where our main machine is, we can see that it is in fact connected to exactly this address. And so we can see the thing is actually connected as we expect. So we have this connection available on another socket here connected to this particular address. That's my address, and that's the remote address. So now we can go ahead and use our remote or reverse shell to look at what's going on that system. So here's what we have on that system. We can change to other directories and see what there's in that other system. We can do stuff. We can even launch applications. We can try launching something like Notepad. Of course, we don't see it here, but it is on the other machine. So here's Notepad. And of course, we usually wouldn't do that if you want to do anything malicious. We try to run other things, but definitely we can do that. So that's it. If we have remote exe here, and that remote could have a different name like CMD, like SVC host, because there's so many of them, it'd be very difficult to figure out that something fishy is going on here. We just need to convince someone on this machine to run this executable. And of course, it also has useful properties regardless of anything malicious. I can now do stuff on that other machine that could be halfway across the world and control some stuff related to that machine, which is of course very convenient. So there you have it. We have this remote shell or reverse shell.